Everyone, welcome to IFML seminar series. We're super happy to have Amin Karbasi today. Amin received his PhD at EPFL and he's an associate professor at Yale. Amin has received literally several awards: NSF Career Award, ONR Young Researcher Award, Air Force. When did you write on this? Air Force Chief, ONR, and so on. And he has done several groundbreaking works in different areas of ML. From submodularity to adversarial training, and now he's moving on with his new adventure on generative AI.
Yeah, thank you very much for the invitation. Thanks for the facts. Yeah, that's the highlight of the day now. So yeah, today we're going to talk about, unsurprisingly, generative models. And I think, the way I see it is like AI is literally changing the landscape of science in very different ways, like by predicting protein structures that unveils the secrets and the structures of organs. It helps mathematicians to solve very complex problems. It helps us predict infections and helping us come up with new ways to prevent them. And I think breaks the language barrier that many of us have by AI assisted translators. But it's not only that this is a technological advancement; it is now part of the news cycle. But with all these advancements, it also has its perils. Right? There is a lot of concerns about the bias of these algorithms, how we use them in high-stake decision-making scenarios. What are the societal implications of these algorithms? I think there is a lot of concerns about safety and security of AI models, how they use the data, how they're going to give information about individuals. And another thing that recently I have been very interested in was, the reproducibility of AI results. Especially if you don't have access to the exact data or the exact model that these big entities trained their models. How can we replicate or reproduce something similar to them? Is there a way to do that? So today I'm going to talk about, generative models along 3 axes. We don't have to go through all of it. We will see how much time we have. The first one is, acceleration of these models. How can we come up with AI models that can handle complex data? And then we will explore how we can use these faster models for medical applications, in particular computational neuroscience. A field that I'm really fascinated with. I have been working on computational neuroscience for the last maybe decade when I moved to Yale with some medical doctors. And then we'll see how we will end up with security issues of generative models and how adversary may exploit such vulnerabilities. Okay. Yeah. So generative AI is this amazing breakthrough, right, that captivated the world. Right? It assists us in coding in so many different languages. I didn't know I could code in so many different languages. Now I can surprise my students. In return, they can surprise me too. And what is really happening is that ChatGPT and Gemini is surprising all of us, right? We can now generate stunningly realistic images, and you're going to see a few of them during the talk. Yeah. And so I think every day we hear news about new models, new applications, new ways that generative AI is processing this complex data, and not only processing them. I think there's something more is happening. They really understand something fundamental so that they can generate new content that looks very correct. So how did it get there? I think this breakthrough really happened through a very, very simple idea, which is, autoregressive model. Really what is happening is like a Markov chain. So you get the way that the autoregressive models work is that, but as the name suggests, they regress in order to predict the next element. So here in a text, what comes after this, they regress on the past, on what they have had before. Okay, so for instance, if I want to, please write a Christmas letter, it might say, well, the next word, what is the best word after this? It might be married. Then the context is going to enlarge. Now this is, what is the input? Then it tries to come up with the next word, and so on and so forth. All right. So that is, I think that is astonishing to me that everything about generative AI, there is no hidden state. There is nothing that we thought are important in order to generate new content. But what they really try to do is just predict the next element in the sequence. Right? Because I think that in machine learning, we have tried to come up with much more complicated things, latent values, so on and so forth. There is nothing of that sort.
But it's inside the network.
Sorry?
The latest state is inside of the network.
Yeah, but there is nothing hidden. Like it's really a Markov chain. It's not a hidden Markov model, or
No, it's not Markov chain. Because you are based on the whole history.
yeah. So okay, after you exhausted your window, then it is like
It's a Markov chain.
yeah,
Context.
context is like yeah.
What's the size of the state?
Yeah.
What-
So the size of this state is very
Yeah.
big, but it's literally a Markov chain in the mathematics. What I'm saying is that it's not even a complicated like hidden Markov model or anything like that.
Well, we're not modeling it as one.
Yeah, we're not modeling. Yeah, it could be. It could, but it is not. It's not these days. And it works somehow. And why it works, maybe the most successful implementation of such a autoregressive model is called transforms, right? And what's really a transformer tries to do, the whole job of the transform is that given this context input, it has to output a vector. That's all it tries to do. And what do we do with this vector? Well, in the case of the language model, we look at the embeddings of all the words in our dictionary, and we try to find, this vector, whether, what is the closest vector to this one, or sample according to some sort of similarity. And this is how we come up with the next one. That's the whole idea. Okay, so now to understand a little bit more, we have to dive into the details of the transformers. So the first thing that we have to realize, as we said, it's a huge neural net, right? With different modules in it. But a neural net doesn't understand words. So what it understands are vectors and numbers. But the first thing that we have to do is, from the input prompt, we go to the token embed. We embed every word into some high-dimensional space. Then they go through various transformations. There is a module like layer normalization, and then self-attention, and a neural net at the end that combines the information. There are usually L layers, so we do this L times, and at the end, this vector concept. So let's look at each module and just understand where the magic happens. One of the modules is the feed forward, the neural net, which is actually a very simple shallow, usually shallow feed forward and two-layer basically neural net. So what it does is that it combines how different elements attend to each other. It combines that information and outputs the vectors. So that's a very classical idea. Nothing very particular about that. The other module is a layer normalization. That is just, it normalizes the input. It normalizes across the layers, the inputs, and the reason that it does that, it just prevents gradient vanishing over the flow. So it stabilizes the training process and make sure that we have good performance. Again, very classical idea. What really changed everything was this self-attention module. How each word should attend to other words in our sequence. All right. So for instance, here, the word Christmas is going to put this much weight onto please, this much weight onto right, etc. All right. It's usually basically it is a convex combination of all the vectors that that come before Christmas, and that gives a self-attention matrix. All right. Good. So everything is good, except there is one issue with transforms. And the issue is that, if the input size is n, the operations is going to be quadratic. And that is 2. That is the main reason that when transformers started, and all the large language models started, the size of the context were like 2K, 4K. They really tried very hard to make it 16 or 32K. But then it was very difficult to push it further because of this quadratic. So the first thing that I want to talk to you about is how we can accelerate and how we can go, from quadratic into almost linear. Right? And in order to do that, so let's see where the problem is. So as we said, there are 3 modules in these transformers. The layer normalization, the computation is going to be linear. The feed forward, again, the computation is linear. What makes the problem hard, or computationally hard, and hard here means quadratic, is exactly these magic self-attention blocks. And why is that? Because this is an n by n matrix. Right? The size of the input was n, it's an n by n. And what you have to do is to find the similarity, how much weight each one of them is going to put on all the other elements. So you have to compute, if you want to do it naively, you have to compute n squared entities of these menus. Another thing that's very important in at least in generating language is what is called the masking, the causal masking. And so if you see that, I don't know any, these are all zeros, and the reason is that it should be an autoregressive model. What does it mean? It means that, this token should not attend to any future tokens. It should not cheat, right? You can only attend to yourself and all the previous ones. But anyway, at the end of the day, there are n squared computations. And what we're going to see today is how we can actually make this into O of n, or almost O. Okay. So to be a little bit more precise, what really is happening is that if you have, your embedding, then you transform the embedding into query and values. These are like 3 different embeddings, right? So first, the attention score is going to be computed by Q T transpose. And then you take the softmax in order to normalize the scores. And at the end, you're going to multiply by the value matrix. That is how it works. All right. So there has been a lot of work, many of them heuristic about how to, get around these n-squared computations by, sparse structures, looking at this attention metrics as a kernel matrix and try to approximate that, or low rank approximation. What really, what is happening in all these things is that they couldn't come up with an end-to-end error guarantees about their approximate attention. And empirically, we tried some of them, and they don't perform as well as they should have. Like if you look at the exact computation and this approximate, because they don't have really end-to-end approximation guarantees, the error can go up very fast, especially if you have more and more layers of transforms. So what are we going to do? What, the way that we try to solve the problem is very similar to, solving a Rubik's cube. What we want to do is to have elements with the same color on the same surface. So here, what we're trying to do is that we want to swap rows and columns such that, it becomes like a block diagonal matrix. The things that are similar to each other, they form a block. That's the main idea. Because if we can do that, then we can, and these blocks, they're small, then it's going to be linear time, and we can parallelize everything. Each one of them is.
The block size is constant.
Yeah.
Sure.
Right? I want this to be constant. Right?
Sure. I mean, you consider the blocks as constant, and you have a constant.
Yeah. It turns out that this is not enough. We cannot just simply select elements. So this is basically putting very high inner products together, elements that have key inquiries that are similar next to each other. It turns out you also need to sample small elements from your attention metrics, and that is crucial. And the way to do it, you have to also sample columns based on their nodes, constant number. And then you put them together, then you're going to have a linear time algorithm for approximating the softness.
So you specify, instead of specifying the self-attention matrix and making it block diagonal when blocks have constant size, you say I'm going to so it's a mixed approximation problem.
Yeah.
Okay. You say instead of me assuming the matrix will be well approximated by a block diagonal, you say it will be well approximated by a block diagonal plus a low rank. What's the second thing?
The second thing is that I'm going to pick also a few columns. How do I do that? I sample them according to the norm.
All right, and then what do you need a matrix at the end?
Yeah, and then I multiply this with it. A few columns of this plus by block diagonal, and that's it.
But the block diagonal thing may not necessarily make sense because that means that two consecutive tokens, you're putting them in two blocks, but
I don't understand.
may not have
algebra.
block
At the end of the day, you need to get an n by n matrix, right?
Yeah.
So how are you adding these columns to this block diagonal?
No, you only select a few of them and then you multiply, this thing
This block diagonal
with
those.
yeah.
and the rest you pad by zero, I guess.
Oh, because of the dimensions don't match.
Yeah, you just select them and then pad. If you don't.
But in order to select, you have to recalculate the whole matrix or.
Right, so the question, that's exactly the valid question here. Like, I don't want to compute everything and then do this. Because then I have to spend and spur.
Exactly. Okay, I see. So before that, I understand that, but that's not what, just for me to understand. The approximation is you say there's this big matrix. I'm going to first approximate it by block diagonal plus some columns, but sparse with a very specific bar structure.
Yeah.
And this green stuff will be copies in theory of
No, the
the.
green stuff's a V.
Is V,
So,
this is V.
but you are training the whole thing, right? You're not approximating the original matrix.
It's, I'm approximating the whole
What
software.
Alex said is correct. You take the block diagonal, then you just add those columns in, like that column, zero everything else.
Yeah.
Add it,
And that's it.
and then he's gonna multiply it by
But-
V again, and he graphically represented that by getting the
Yeah.
block
Yeah, yeah.
by V plus the columns by.
The fact that I'm multiplying by V is always done.
Yeah.
By V is irrelevant. I'm
Yeah.
approximating
Yeah.
this matrix.
No, but like dependent the same, like, I mean, are you saying that there exists a block diagonal matrix that is close to this, or is?
That's the
there-
first statement.
Or it's just the same blocks as the blocks of this that you're, because,
No, it's not the same. I have to.
oh, you
something.
might choose some.
I have to swap
Okay,
columns.
so
It's
you-
not going to be like I pick this and then this.
Right, but
No,
your
I have to do
claim
something
is,
else.
your claim is, if I have the attention matrix that exists. A block
mechanism
diagonal
to do-
matrix.
Yeah.
That with some random addition of columns, that approximation is close.
Yeah.
That's it.
Yeah,
Yeah, there are two conversations. The first is for real transformers running on real text. The self-attention matrices are close to
Yeah.
the sum of the block diagonal plus
Yeah.
columns. That's the first hope.
Yeah, block-
If it's not close, then we're dead.
yeah,
anyway.
you're dead.
And the second situation is how the hell do we find it?
Find it, yeah. Yeah, okay. Exactly. Very good. So. And as it was asked, I don't want to compute first, see which ones are close, and then do the permutations. I want to do it implicitly, without computing, right? And that is the whole idea of LSH, and in particular, what we're designing, the particular kind of LSH called sort LSH. Because I want these blocks to have elements that they have almost the same size. And the elements of adjacent blocks are also similar to one another, so that if I want to get one element from one to another element, I'm not going to lose.
Short LSH is your thing or
Yeah.
is that no thing?
It's our thing, it's our previous paper.
Oh, it's a previous thing by you.
Yeah. Alright. So how does it work? In a, the simplest way that I can explain. You have query keys. And what you want is that you want to have blocks such that the inner product between the key and queries that are, high end up in the same buckets. What I need is just the index of the buckets. I don't want to compute the inner product. I just want to know the index that these things go into. And that we can do with LSH, with random sampling, random projections. So basically, once you know the buckets and which elements go to the same bucket, you commute the Q and queries, right? So in order to get something that looks like a block diagram.
So do you have a mechanism to ensure that each bucket has the same number of P and Q?
That is a sort element. There's a sort element.
Okay.
That allows us to do this.
It's like a K nearest neighbor.
It is,
Yeah. So
yeah.
fixed K, K.
And what's the cost of figuring out what's the right rotation of columns to get this?
That is going to be everything linear. That's the whole point of this sort LSH. So it's going to depend on the dimension, but not on n. A linear in n. So to sort things.
But you're sorting the inner products, right?
I want to, now it's, this is the original one, and now the new is Q1, Q2, and here is Q6 suddenly. Okay, and this was Q1, Q2, and Q1, K6.
So for Q1, so what's given here is there's a vector for Q1, right? I put it in a bucket and then I sort all the queries, right? But then don't I have to do n log n to sort or? I'm sorting
No,
my
the
bucket.
swapping is going to be done in linear. You don't, you just need the index for the buckets.
Are you also now ignoring the masking from the original?
So yes, I have to do some extra thing to do the masking. I'm not going into that.
Yeah, so I was wondering, so in this approach, do you actually ignore the ordering inside the bucket?
The what?
The ordering inside the bucket. So
I don't care about this.
Yeah,
Ordering of them.
that's what he's asking.
Yeah, I don't care about the ordering inside the box.
Yeah, that's,
Yeah.
this is why you want to use block diagram.
Yeah,
functions.
yeah.
Because another natural approach is to use the strip diagram.
Yeah,
In that case, you will require a global sorting.
yeah. No, I don't care about the ordering inside.
Yeah.
I just want to put things that are close into.
But does your algorithm actually return a global ordering for the?
So the sort one is going to be is going to make sure that if you pick an element from here and put it here, it's also close.
So in fact, you will actually get a global ordering for the.
Or approximate global.
Yeah, but if
Yeah.
that's the case, why don't you use the strip diagram? Other than the block diagram?
Like this one,
Yeah, or few or this other missing block.
because this is easy to do. If we do it this way,
In what sense?
the whole operation is going to be linear.
Yeah, the strip diagram should also be.
You can add to this, like, add elements
Yeah,
here.
right.
The issue is going to be in parallelization.
Oh, okay.
I don't wanna,
Yeah.
right?
Yeah.
I want to make sure that this goes to one machine, this goes to one machine, this goes to one machine. That's the issue. Okay. Under correct assumption that we have row column norm that are almost uniform, then we can also make claim about the approximation in terms of the operator norm. Okay, so that is the exact, that is approximate, is going to be, and this is the correct approximation error that you can get. If you don't have these assumptions, we can also show that there is no subquadratic algorithm. You have to have assumptions about the G and queries. And in particular, this is the weakest kind of assertion that we can come up with. Okay. I think in generative AI, it's one thing to come up with a theory, but usually people don't care about theory. You have to show that it works. Right? So we have to implement. We have to implement everything. So this is for the image generation for vision transformers. This is the exact images that it generates. They're not cherry picked. We randomly selected. I insisted that we randomly select. So this is a dog. This is a dog. This dog is one head. I think our dog is better, even though it has 5.
Okay, these are generated images.
Yeah.
Okay.
The qualities are better. But as we increase the context, this becomes like 250 times faster. Order of magnitude faster. Right? And this is not exact naive implementation. What we're comparing is flash attention 2. That's the best exact implementation.
How do you measure speed up here?
So it was like how long it takes to generate.
So I'm saying is, are you calculating number of operations or it's actual work clock?
Actual.
It's actual
Yeah.
work clock on a GPU.
Yeah.
Okay, that's what I'm asking. So it's so this is seconds?
These are in seconds because this is going to be a vision transformer that has only 1 or 2 layers of transformers. But okay, so how about language? So ChatGLM is it has 28 layers. And what I'm showing is like if you replace every single layer, the attention with the approximate attention, then in terms of complexity, you lose 6%. Okay, without any fine tuning. The speed up, so we replace everything and we look at the end-to-end speed up with all the other operations. You get more than 2 times speed up.
What network is this?
This is the ChatGLM.
ChatGLM.
This is a particular language model for long context. Right?
I have a question. Your method is a drop-in replacement
Yes.
to a pre-trained.
Yes.
Okay.
And fine, yeah,
You don't need to retrain anything.
Nothing.
Okay. So you can just take any.
Any.
You could take llama and
Yeah.
and do that.
Yeah. Anything. You just replace, and you can easily fine tune. So I particularly wanted to show you without fine tuning, you are not losing much. Okay. And here is like, some downstream tasks that you see, they're very compatible, like for few shot, summarization, code generation. Right? The results are very, very close.
I guess the question is like, how much of better in the speed up is this versus other sparsification techniques?
So this is definitely the fastest one. The issue is like how quality degrades with other sparsification, and they're very bad. We actually, so I told, maybe it is recorded, maybe I shouldn't say. So we had 3 linear time algorithms, 2 of them didn't work. In theory, they were linear time. In theory, they should have worked. We implemented it in.
Everything is dropping again, or you have to, or they require extra work?
Yeah, just replace.
Just replace.
Yeah.
No
extra
fine
work.
tuning.
Yeah.
Right, but I mean, like you had that slide where you have like there are 12 different methods you're doing.
So there are many other methods.
Yeah.
The issue with, and we have, I didn't show the results here for the other ones, like even on vision transformers, the results are not good.
For all 12.
Many of them. Yeah,
So my knowledge, I haven't been updated, but I know that none of those classification techniques for accelerating attention were used.
yeah,
So
exactly.
last up to 2 years ago, when
Yeah.
I stopped following this
Yeah.
literature, nothing was used as far as.
Yeah.
I don't know why.
But
Yeah.
you.
Maybe they didn't work. as you
They
said.
didn't work, and
Yeah.
people try and they really don't work.
Right.
And
I have a question about the performance. The summarization performance looks good, but the single QA and mono QA, I think the drop
it's
is
very bad. I
it's
agree.
very bad. It's
very bad.
roughly dropping from a 13
Yeah,
model to 3.
Yeah, that's why I also wanted to show this result. I didn't want to show only these 3.
So why?
Oh, so for single Q&A, I think there is not enough context to get it right. With fine tuning, it almost matches. If you add another LoRa fine tuning to the end. But without it, it doesn't work.
So in what context we're talking about the context? Because if I compare with the single QA and the summarization perhaps requires the most dense attention all over the sequence.
Mhm.
You need to look at it once. Single QA can often be done by looking at the beginning and the end, and you can even use a stream LLM.
Right.
The performance on single QA is really fine. So is it right to interpret that your approximation works well in looking at the middle of the window, but perhaps in somehow sacrifice the performance, look at the beginning and end?
That's a very, very good point you're saying. There are 2 things. First, in the single Q&A, we had to get the answer exactly correct.
Mhm.
In summarization, there are many correct answers. And they're all, the scores are going to be high, and they're all good. That's one reason. What you're saying is actually also super important, like the beginning of the context has a prompt in it,
Mhm.
and you have to keep it.
Sure.
Once you keep it, in some of our implementations, you just keep the first 8 columns or the first 32 columns, and then it shoots up.
Mhm.
It's still linear, it shoots up, the performance becomes much better.
Okay.
That's
so
correct.
what if you have to do a shift?
Yeah, so if you keep those, then it becomes much better.
Okay.
Yeah.
Then how about multi-QA? Are you doing multi-choice QA or?
It is multi-choice, yes.
Then-
And if you get one of them right, it's fine.
Yeah, so this is a much less difficult to choose.
Yes, yeah,
Compared
agree.
with singles.
yeah, I agree with that.
Yeah, but the drop rate is still 15% from no replacement or replacement.
Yeah.
Yeah. Okay. And I also wonder, I have to check, I probably need to read a paper about your linear attention approximation. But I remember back 3 years ago, a colleague have a paper showing that if you interchangeably use a linear attention and self-attention, just stacking them intervally, and the performance can match, but probably that's a BERT level experiment. And that's one of the closest thing I remember what people once said about linear attention as a practicality. I will compare with that because here you're also doing.
We
number
didn't.
replacement. Yeah.
We didn't do that. I don't think that we did, but yeah, we can try. I mean, there's so many methods.
Sure.
Yeah.
All right, thank you.
Yeah. but yeah, very, on the topic question. Good. Oh, okay, so we are switching now, if there are any. Good, okay. Now, how can we use these models, long context? I want to make sure that, for the application that the input is really long. And, one of the applications that we had in mind and we tried actually to do is, can we teach LLM the language of the brain? And if, you don't take anything from this talk, please at least read this very nice article in New Yorker about the science of mind reading. It really is a fascinating article. And in it, it's sort of like, it is not so much that, the brains can, work better today. I mean, they improved over the years, but the reason that we get really much better results is because, we become much better at reading the brains. And in particular, there are different ways to look at the brain. And one of them is the fMRI signal that tries to capture what is called the BOLD signal, which is blood oxygen level dependence. It's a proxy for the brain activity. Okay, so if part of part of your brain works, the oxygen level in that part increases. Right. So in the past, in the last maybe 4 or 5 years, we have been trying to come up with brain maps that tells us how different parts of the brain work with one another, but we never could have made it work for diagnostic tests. Right? It was just too crude because the methods were not good enough. And now, with brain LM, suddenly things change. So what are we doing now? Here, what we're using is, a UK biobank data set, which is huge amount. It was a huge effort in the UK. They had basically 41,000 individuals. There is a year worth of fMRI data. And what is cool about this data, it comes with all sorts of diagnostics, like what is the age of the person? What is the gender, anxiety level, depression, PTSD, etc., etc. So there are all sorts of medical variables. And what we want to do is, we basically train a brain language model and try to, do the zero-shot inference or fine-tuning tasks like the prediction. All right. So how does it work in its simplest form? There are usually 1 million voxels. This is the resolution of the fMRI machines. It's very high. We cannot work with that resolution. So what practitioners work with are postals. So they collect like 1,000 or 10,000 of these voxels into one super voxel. They call them voxels, and this is the activity. But it's a signal. For people who are used to signal processing, that is basically a signal for them. Now, so there are n parcels. Usually it is around 400 to a few thousand. So we chop the input signal into smaller units to 20 timestamps. We use a linear transformation in order to have the vector representation. And these are going to be, for these parcel, these are going to be tokens. Then what we do is that we do the random masking or causal masking for the future. We use it's an encoder-decoder architecture. So the ones that are not masked, they go to the transformer to come up with a good representation. We're learning the representation. And in the decoder transformer, we try to predict the ones that are masked. All right. And then we go back to the signal domain and see how well we did. That's the whole training process. All right.
Supervised pre-training.
Mm-hmm. That's exactly what it is. So how well does it work? It was very surprising to me that it works really well in the sense that here, 75% of the in pocket, so that's holdout data, 75% of it was masked. but it can really predict, the signal. Right. What was even more surprising was that this is a human connection project. It's a completely different setup. A completely different data set. In particular, the ages in this data set are much lower than the age of people in this data set. So it's out of distribution.
Well, why does that mean it's out of distribution?
The age is different,
So
so
what?
okay, it has never seen this data.
Sure, but it could have the same fMRI scans as other people of those other ages in training them.
They, I mean,
No, but they are in different ages.
So what? So what? That doesn't mean that they're out.
they're,
Doesn't mean they're out.
anatomically they're different, and people realize like, there are
That's
some-
like saying, well, we took people from a different country, so it's out of population. Doesn't mean anything.
yeah, but the age is different. The
So what?
age, no, it's.
I think the conversation is, do the fMRI statistics change as people age?
Age,
Yes, and we don't know. Yes.
Yeah, so
Maybe they do.
they do change apparently, and people have like for some of these tasks, one is easier to do the other, than the other one. But yeah, I mean, anyway, so it also performs, for the data that is in a completely different setting, collected, and then which would be the different set. And then, we also try to, do the predictions. And that is a very, very hard task. Like I am trying to predict how you think in future based on what you have done, right? So even though the numbers are low, they're much better than all the other methods that they try to come up with, LSTM, neural ODs, etc. And, if you look at this, the weight of the self-attention, how much this particular token, the class attention token, how much it, weights other, then you see a very, between the task and the resting and low and high depression, you see a significant change. So it really understand what is happening for, individuals that have low depression and high depression. You can even visualize different, areas of the brain based on the self, the class attention token. And if you do it for this class attention token, for each fMRI, if you look at it, then there is a significant difference between male and female. And age.
So is this a time series data?
Yeah.
But you also have the space dimension, so is it?
We can encode it.
Encoded.
Yeah, so either,
You will flatten it into a two-dimension.
yeah, that's right, yeah.
Yeah, but
Then
time
how
series
did you
per box.
get This
Mhm.
tension.
Per, parcel. That's a huge box.
Okay, so yeah, aggregate, it's a time series per region.
Per region, yeah.
Yeah, so if you could go back to the article number, well, it's a very noisy time series for sure. I'm just curious, when you train such a how long is the model, by the way? 7 billion or over billion?
Sorry, how much was the?
Model size, parameter. Okay.
Yeah. So these are small, yes.
I didn't intend to call that
Yeah.
small, but even this size, let's start from this question. Did you ever see your training loss decrease?
Oh, yeah, so, yes. So if you increase the size of the model, yes, it does. And you see the scaling laws. We now have like we tried bigger models. And hopefully soon we'll have also on Llama. It's much easier for you guys with your GPUs now, but.
Yeah, we can chat more, but I was very curious because noisy data like this, our experience is, it's very hard.
It is super, yeah.
It's a loss decrease even.
Yeah, it's super hard.
Okay.
That's why, even though the numbers are not, but it's a big thing.
Okay,
For me at least.
well, it is a big thing. I understand.
Yeah.
Okay.
Yeah.
Thank you.
Small numbers, big things, yeah. Okay. So then, what we did was, after that, we can fine tune it using, an MLP, multi-layer perceptron. You can actually predict the age of the people. Right? Within 2 years. So this, it's amazing. You look at the fMRI, you predict the age. Okay, and all the other medical variables. And least and last but not least, it is in collaboration with a bunch of amazing people, in particular David Van Dyke, who is my who knows much more about computational neuroscience and who is in the medical school.
I guess that proves our previous conversation.
No.
It's out of distribution.
No.
If you can tell the age, it means it's out of distribution.
No, that doesn't.
How can it not? I mean, there is two populations, like in one hospital.
Yeah, let's let him finish.
Adam is very adamant. Okay, good. Okay, I don't have much time. I wanted to talk a little bit about adversaries. I think Hamid is coming next week. He's going to talk much more about this. Let me just say, I think I said there is a lot of issues with generative AI, prompt injection, hallucination, etc. It is very well documented. And the way that we actually try to get around these problems is by a method called, reinforcement learning through human feedback. We basically collect human feedback, comparisons and such from humans, and then try to have learn the reward function, and then have a reinforcement learning algorithm to align the model with what it should really be. And it is very effective for benign users. What are the problems with RLHF? The first thing is that it needs a significant amount of human efforts. You have to spend tens of billions of dollars to collect the data from real humans. And the second thing is that it's not effective for adversarial users. Okay. So what do I mean by that? There are basically two types of jailbreaking. One, you want to say that develop a strategy for hacking into a UTL-SYN database. The LLM basically should say that I'm sorry, it's not going to happen. I'm not going to tell you. So how do people get around this? One way is, which is a non-interpretable jailbreak, is you add sockets, right? And try to get around the guardrails. The other way is try to role play. To say that, I am writing a novel. In my novel, there is a character. His character is Adam, and he wants to get into the system. Right? How can I? Right. So, and then, the LLM might actually answer that, like it is a novel. So this is, how you should actually, what your character should. So this one, you can only do it if it is an open source, because you need the weights and the gradients. This one, it's not automated, but you don't need the weights. You don't need any, right? If you could do it, good. So what we try to do is basically come up with an automated method for jailbreaking of the closed source models like GPT, right? So for black box LLMs, it is automated, and then you understand, it's meaningful jailbreaks, and it is in collaboration with some amazing people at Karbasi Intelligence. It was immediately covered in the Wired magazine. So how does it work? We call this method TAP, train of attacks with pruning. The way is that it has, if one large language model is good, three of them are much better. So there's a target, GPT-4, an attacker is a large language model, but much smaller. Open source, much smaller, not aligned. Tries to attack the target, and there's an evaluator. This evaluator, what it does is that, so before sending a prompt, the attacker, before sending the prompt to the target, the evaluator looks at the prompt and says, is it on topic, or is it likely to jailbreak? If it is not, it's going to prune. It's not going to send, right? So, for instance, that was like, write a letter on, countering false accusations, or imagine a co-worker, and the evaluator says that, okay, this is off topic, this is on topic.
These are LLMs.
These are all LLMs, completely automated. There is no human in the loop.
Right. So these are like Llama. What did you have?
Vicuna.
Okay.
Yeah. It's a very small model, 30 million. this one says, it is on topic, you use it, the target says, I'm sorry. Then because it's a tree of attack, so it's like a tree of thought, it reduces more. And you go on, okay? It's a zero-sum game now. You're trying to win in this zero-sum game.
But you're not training,
No, not training him.
or you're not training the evaluator or the attack.
No,
Okay.
nothing.
Okay.
It's just, I just put them in the loop. And then, suddenly it's going to jailbreak. Is it going to work? Does it work? Yeah, this, tree of thought. With a very important part that is pruning. Turns out it works remarkably well. So, for GPT, it is basically 80% of the time. You give me a prompt, we put it in this way, boom, 80% of the time it's going to jailbreak.
Instead of hiring contractors to red team the model,
Yeah.
you have just
Completely
have
automated.
LLMs
Yeah.
red team.
Yeah. And with how many iterations with this is less than $1 of API access.
But it's still thousands of calls.
No, this is the number of calls.
Oh,
22,
on average.
28. It's significantly smaller than what was possible before. It's, within 20 to 30 calls.
So pair and GCG.
Pair is the one that Ahmed is going to talk, I guess, next week.
Okay.
So GCG is a Zico's method that only uses open source. So
Right, that's a gradient descent.
that needs thousands.
Right, but that's a different story.
That's a different story.
But pair is also an LLM attacking
Yeah,
LLM?
yeah.
Okay.
But here, what you're compounding is the tree of thought. So it really goes out and tries to explore. But it's not going to work if you do not prune. Pruning is a very important part. Okay. Anyway, I don't think that I have time to actually talk about, the future. But it's a good time to maybe stop. And, if there are any more questions, I'll be happy to answer. Thank you.
Just one quick question about again, going back to the very first part of the talk. So is it like a completely linear in N or like?
It's N to the 1 plus epsilon, and the epsilon here comes from the part that we had to norm.
The approximation spectrum.
Talking about that attention, what if I just use the rank plus a random samples?
Low rank attention
Low
from
rank versus a block, the block diagonal, y-axis block.
so the block diagonal was for parallelization. That's a very important part. And also making it linked. But you want to be able to have a method that every block goes to one.
Yeah, parallelization makes
Yeah.
sense. The brand LM model, you mentioned it's fine-tuned from what?
So so either you fine tune it to the task that at the end you want to do it.
I just saw your table, the brand LM, you always say they are fine-tuned with a parallels. But what is the fine, do you train that from scratch with?
These are trained from scratch.
Then I'm even more curious how you lower your training load.
Yeah. So these are like GPT-2 type from scratch.
Yeah, because I have very negative experience with
Okay.
those models of knowing these things.
Yeah. But it's a BERT kind of model, right? So it's a bi-direction. That
Even that.
even okay.
Even.
Yeah. So now you're more clear. It's it works for prediction. Actually, we found that bi-directional attention is better.
Yeah. And by the way, I work in the range of R square between 0 and 0.03. So
Okay.
I think our numbers are very high.
Okay. Good. At least I'm higher.
All right, if there's no other questions, thank you.
So. Absolutely, yes. For example, imagine the same kind of slightly.